Okay, welcome back. Now we have Andrea Sportiello, one of the best apples of Sergio. Well, so he's going to talk about integrable models and algebra of symmetric functions. Andrea, the stage is yours.
Thank you, Eric, and thank you everybody for being here. And in particular, thank you to Sergio for being the very reason for us to be here. And this is a talk that is not talking about something on which we worked together. It's something, in fact, I've been doing recently with Luigi Cantini. But it is, in a sense, a topic that it's a witness of the spirit by which we have done research together, which is research for the pleasure of doing research, not for the pressure of writing papers and having grants or whatever, which is we want to solve questions, we want to understand how things go. And it is also somewhat similar to the talk of Alan. There are many conjectures, very few proofs, and not even as smart as Alan's ones. But I hope that the conjecture will be in your taste and you will like them, or at least they will spark some thinking about. And also somehow the research topic will interlace with the personal experience with Sergio in some way that I will tell you all along the talk. So let's start with the topic at 10 today, which is, okay, now it's not working anymore. No. No, non funziona. Devo cliccare il mouse. So, something which is in the topic is the Razumov-Stroganov conjecture, which is in fact a short name for a set of conjectures which has accumulated in the early 2000s around two different integrable models, which are the O1 dense loop model on a cylinder in its first incarnation, and the fully packed loop model, which is another way of seeing the 6-vertex model on the square domain. And it can be understood in purely combinatorial way, in a very graphical way, because those are integrable models at their so-called combinatorial point. And it's a correspondence between topological observers, in a sense, which are called the link patterns. First of all, what is a link pattern? A link pattern is a connection among the two endpoints of a disk or of a segment, which is non-crossing. It is a pairing, and it is essentially something like that. You see what it is. So there are Catalan of them, as well known, and they are in bijection with those things that I should call integer partitions, 3, 3, 1 in these examples, which in this case are boxed in what I call the triangular integer partition, which is the maximally one that you could do here. And so this is Catalan and possible topological observables. And they arise in the O1 dense loop model in a natural way, because you can interpret this semi-infinite cylinder. You can draw it as a disk in a sense. You can fill it with these two ties just by coin tossing and do a configuration like this. And then you just follow the path that touch the boundary. And from that, you build up a link pattern and you write it down. So you have some probabilities for this. It is not clear that they are rational numbers, but they do. And you write them down and put them in a corner for a given value of n. And then you take a square of size n, and you fill it in all the possible ways with these 6 tiles, uniformly among the possibilities that there are, that now they are infinite number. And then again, you have, for example, the black termination in this boundary condition that I should call it domain wall boundary condition, which means that black and white alternate along the boundary. And you follow only the black. For example, from here, you go there. And so you have, by another recipe, yet again, a link pattern. And now you write down the probabilities of these link patterns, which are, of course, rational in this case, but they do not seem to have any more symmetry than just the symmetries of the square. Very well. What happens is that these two lists of Catalan and different values summing up to 1 do coincide. This is a fact that has been first observed by Razumov and Stroganov in this very incarnation, and then has been proven by myself and Luigi Cantini around 2010 for this domain, and in fact, a whole class of domains, which we call dihedral domains. You will see them in a moment. And that's nice because the two symmetries and the two properties of the two models, they come together. For example, there is this enhanced symmetry here on the fully packed loop side, which means that you have this rotational symmetry, which was not there to start with. And that one was having already an explanation due to Wieland in early times, in 2000, that is very bijective. There is a sort of bijectively show that these 6 configurations and these other 6 configurations are related because they correspond to link patterns which are one rotated of the other. And this Wieland giration operation, which is the bijection that I'm talking to you, has been a crucial ingredient for understanding the proof. And also, it has suggested us to look at this set of dihedral domains, which, for example, these 3 bundle domains is another representative. So you have these probabilities, which are 1/7, 1, 1, 2, 2. And here again, you have 2/14, 2, 2, 4, 4. These are just proportional vectors once you normalize them. Very well. So these up to for the good news. And now we have 2 bad news. Wieland giration works for the white and black link patterns simultaneously, and the counting of the loops, black plus white, altogether. So it is natural to expect that if you really want to squeeze out all the possible consequences of this tool, you will have some Razumov-Stroganov type of conjecture involving black and white. But we never could cook up such a model on the FPL side and on the O1 side, sorry. This would be something like a rotor model. There is an integrable model of this sort called a rotor model, but it doesn't seem to have the kind of Razumov-Stroganov conjecture we want. So we don't know how to make a black plus white Razumov-Stroganov. And also, there is a whole half of the story of Razumov-Stroganov conjecture, dating back to the original papers of Razumov-Stroganov, that works with so-called vertically symmetric alternating time matrices or fully packed loop configurations, which are, well, this is horizontally symmetric, but that's the same. So, which are configurations which have an axis of symmetry, and so link patterns which are on a half disk, if you want, or on a segment, and O1 configurations on a strip instead of a disk. And you have a very similar type of conjecture, but we have no proof for them. We have a number of tools, and they don't seem to apply in the same way. We tried to do something and couldn't make it. So yet another bad news is that we kind of know which are the domains which should be there. So this is another type of situation in which you expect to have just proportionality. We know exactly which is the set of dihedral domains, of vertical domains, which are the analog of dihedral domains, but we don't know why, and we don't have a proof. This dates back to 2010, 11, 12, if you want. We have been thinking about that for a long time. Sometimes we come back to the theme. And then some time ago, we look at that in a different way, which is a bit crazy. As I write there, we are smashing together the two failures that I mentioned. We don't have a vertical Radsunov-Stroganov proof. We don't have even a conjecture for the black plus white. But we now look at the topological observable that you would have in a black plus white Radsunov-Stroganov, and we look at that for a vertical domain, which is this one, and see what happens. This is something that you shouldn't be advised to do. But, well, we did it. And what you get is the following. You see, in this case, you have these small arcs on the boundary because it is a vertical domain, so there is a boundary. And these arcs may be white or black. Let's divide the configuration according to how many white and black you have. So there are 3 with both white, 6 with a black, and 3 with 2 black. And these 3 ones, they have pi black and pi white, and number of loop, which is this, and 0, with probability 1/3 or 2/6 if you want. This, and 0, again with probability 1/3, and this, and 1 with probability 1/3. So there is a proportionality of this 1, 1, 1 vector in these 3 different sectors. So this link pattern is the black link pattern. So 1, 2, 3, 4, they are connected this way. While here 1, 2, 3, 4 are connected that way. And red is for the white. Sorry, because I cannot use white here. And 1 is the number of loops. So you have a white loop here, a white loop here, a black loop here, and a black loop here. So this is the number of L is the number of loops, and this is the number of black arcs on the top. Well, I need to be short, we know. So a first conjecture, without talking about something we knew before, is that there is a factorization. This 1, 2, 1 is just the binomial distribution, as you have guessed. So there is a factor 1 plus y to the power n overall component-wise for this triple enumeration for all values of n. Let's say that this is conjecture 1. We don't have a clue on how to prove it, but let's take it for granted and let's get rid of y. So we have only 3 things left, which are the 2 indices for the 2 link pattern and tau to the number of loops. And so we can record this counting of configuration into a table with a black and white link pattern of polynomials in tau for the counting of loops. And as I told you, the link patterns can be bijectively be related to integer partition, box, and integer triangle. And so I do that. And I also record the number of squares in the integer partition, which is 0, 1, 2, 2, 3 in this case. Many conjectures are coming. This is the big table at n equals 4. And this is a large example. So out of this configuration, you build up the black and white link pattern. 1 connects to 6, so I have a 1 to 6 here. I construct the integer partition, which is a 3, 3, 1. And then you have a 4, 2, 2, 1. The number of cycles is 2 because you have this one and this one. So you get a tau square in this big sum of configuration into this counting polynomial. First conjecture beside conjecture 1. We know the degree. And the degree is well described by the integer partition. It's the sum of the sizes of the integer partition minus the box in triangular partition. In particular, as these guys are obviously integer valued polynomials, the degree is 0, the polynomial is 0 if the degree is predicted to be negative, because there are no negative negative degree polynomials. Conjecture 3. These polynomials have definite parity. If the maximal degree is even, the polynomials are even, otherwise they are odd. Conjecture 4. The table has 3 involutions. It is symmetric in lambda and rho, and then it has the symmetry that swaps rho with rho prime, lambda with lambda prime, which is taking the transpose of the integer partition. And so there are various ways in which you can do that. All these ways give a symmetry, and 2 generators of this z2 to the cube group are somehow easy. One of them is just proven, and the other one will be a corollary of conjecture 1. But a third generator, this one, remains mysterious. And I'll come to back in a second. I'm done with time. And then conjecture 5. The integers, the polynomials of degree 0, are the Littlewood-Richardson coefficients. They really do, even at size 4. And this has been checked up to size 5 or 6, I'm not sure. What are the Littlewood-Richardson coefficients? Here I have to cut a lot of the talk, so I'm sorry. I hope you know what a Schur function is. Schur function arises as a linear basis for the ring of symmetric functions. And, well, it's a long story. Sorry about that. Schur functions in a supersymmetric alphabet are constructed in a certain way, and they have a special property that if you take the transpose of an integer partition being the index of the Schur function, you are exchanging the bosonic and fermionic variables in your supersymmetric alphabet. And a nice fact is that Schur functions, sorry, I skip again a lot, are described by another simple statistical mechanics model, which is Lorentz-Stielings. And also the skew Schur function do, but I didn't tell you what they are, so it doesn't matter. So an even simpler version of this 6-vertex model that we have seen before. And it is a model of red and blue lines that make a bundle, cannot cross the blue with the blue and the red with the red, but they can cross the blue with the red jumping over the blue in a certain way. And the way is described by these weights that I describe here. And xi is the variable x of index I if this tile is at height I. When you play this game, you end up with partition functions of statistical mechanics model, which are described by the sequence of black and white dots on top and bottom. And these partition functions are the skew Schur functions with the given alphabet. And the case of supersymmetric Schur functions is done in a similar way by using the yellow tiles for the bosonic variables and the green tiles, which are the reflected version of the yellow tiles, for the fermionic ones. So you have a statistical mechanics tool to describe in a very concrete way this family of polynomials, which are important in the representation theory of GLN-M and in the algebraic combinatorics of rings of symmetric functions. And this is another way of constructing the same functions. I skip this, but there are some transfer matrices for the yellow and green tiles that construct this Schur function at an algebraic level, which means you can understand the 2 boundary conditions as a bra and a cat in a Hilbert space notation, and the single layers as transfer matrix in a transfer matrix approach to this kind of systems. So this is just an algebraic reformulation of what we have seen with a lot of consequences. And there is a beautiful idea of Paul Zinn-Justin, which is to understand that the Littlewood-Richardson coefficients can also be described in this framework. The Littlewood-Richardson coefficients are the structure constant of this ring. So I give you a ring of functions and a linear basis. So what you're left to do is to describe how do you expand the product in the basis. And the coefficients of the expansion are the Littlewood-Richardson coefficients. And if you write down this equation and you study a suitable higher rank Baxter-integrable vertex model, you realize that by making commutation of transfer matrices, you can describe that the partition function of this system is the same as the partition function of these systems. But these two systems have many frozen regions and two non-frozen regions here, which can be interpreted as Schur functions because there are only two colors there. White and green here, white and red there. This messy object. And here on the other side, you have one supersymmetric Schur function because you have only red and green. So you can realize that you can construct these, and these pieces in this geometry. So the messy object here must give a combinatorial interpretation of the last ingredient. So we recognize that these counting of configurations, these special partition functions, are the Littlewood-Richardson coefficient, something that was known to Knudsen and Tau. Very well. So we have Littlewood-Richardson coefficients popping out conjecturally in our tables. We know that Littlewood-Richardson coefficients can be described by integrable models, but we have all the other polynomials of higher degree that we don't know how to describe. So we want to deform Schur functions, make them richer, in order to find some new structural constants whose deformation may fill up the rest of the table. Long story short, I will skip a lot. There is a kind of way to do that, that is constructing a deformation of the weights here by putting a minus tau in the good place. And once you do that, you construct new branching rules, Perry rules are called, and a new deformation of these ties that I told you, that gives you a new way of constructing monomials. And these new functions can be recognized to be some alpha beta Grothendieck polynomials that kind of exist in algebraic combinatorics. Let me skip of these. Okay, we have explicit formulas for them. And these new Grothendieck polynomials have structural constants that correspond to the highest degree monomial in these polynomials in our table. It is a partial result, but it is much more than the bare Littlewood-Richardson coefficient initial conjecture. And as a bonus, we can prove that at least this extra symmetry is consistent with the transfer matrix trick of algebraic description of Grothendieck polynomial in this case that we have, which is a non-trivial fact because this is a very non-trivial symmetry. And as a final bonus, we have also a deformation of the Knudsen-Tau puzzle approach, which is, so these are the original Paul Zinn-Justin way of counting Littlewood-Richardson coefficients when they are Littlewood-Richardson for the Schur functions. And if you add an extra type of tile, this kind of weird hexagon, you have the new Littlewood-Richardson coefficients that count the leading term monomial in this whole family of polynomials that fill the bottom right part of the table. Well, that's a long story, and I only sketched you by skipping a lot of proofs and even a lot of bad definitions. Sorry about that, but that's a really long story. But the point is that I enjoyed a lot doing research with Sergio, and I enjoyed a lot staying with him all all this time and essentially having a life together at several levels that was passing from the research and writing papers together and also to having advice on life and things to do. And every time you have a doubt on what to do or a remark or a discussion about things going around, it was always there. And it was a pleasure to do that. And it has been an important ingredient on the fact that I developed a pleasure for doing research myself, various topics. And I want to thank him again for his special role in my life and the big luck that it has been working with him instead of dropping somewhere else. And I am sure that this is a feeling that is shared by many. And thank you again. And I am much more messy than you in doing the talks. I couldn't learn that, but.
Thank you, Andrea. Questions?
It's hard to have questions if you don't have definitions.
No technical questions. I have a special question from Luigi Cantini, directly, who is asking when is the paper going to appear?
Well, the paper is going to appear when Luigi will finally prove all these conjectures.
Okay, so your conjecture maker is the conjecture prover.
Well, all this proven.
No, seriously, other question? Okay, so let's thank Andrea again.